Good morning, everyone. It's a pleasure for me to present this keynote lecture for the attendees of International Conference on Computer and Knowledge Engineering. I've presented this talk several times before, and I've revised it substantially since its first offering. In fact, it started with the title 7 Key Ideas in 7 Decades of Innovation. But now it's 8 Key Ideas for in 8 Decades of Innovation. And the latest incarnation of this talk I prepared for IEEE Computer Society's Distinguished Visitors Program when I was selected as a distinguished visitor. And I've given this talk in many venues. The talk contains a lot of slides. I probably won't have time to cover all of them today. I'm going to skip a lot of the slides, so don't be concerned if I go too fast, because the talk has been designed so that it can be given in different formats, anywhere from a 45-minute talk to an hour and a half, sometimes even 2 hours. So there are too many slides for a 1-hour talk. I gave this talk as part of the 75th anniversary celebration for IEEE Computer Society. It's a good talk for that purpose because it's a historical talk. And in fact, it covers the 8 decades it covers. It's almost the same as the history of IEEE Computer Society. So I was asked to give this talk as a historical talk. Okay, so the bulk of the material in this talk come from 2 of my textbooks, one in computer architecture, 2005, another one entitled Introduction to Parallel Processing, published in 1999. Both of these books are now outdated, given how fast computer engineering moves, but I've maintained a list of updates to the books, and eventually I'm going to publish revised editions of both books. So in this talk I'm using some of those revised material as well, not just material from the books. Now, we are all fond of making top N lists. In particular, top 10 lists are very popular here in the United States. And people like to sort of indicate their preferences for movies, books, recipes, sports teams, colleges. So one of the things we have here in the US is an annual list of the best colleges. And if a college ends up in the top 10, then they can boast and be happy about it. Of course, whenever somebody prepares such a list, other people may disagree about the selection. So typically what happens if you, for example, prepare a list of top 10 colleges, there are likely 3 or 4 colleges that appear on everybody's top 10 list, but the rest of the list typically differs from one person to another person. So here basically what I'm doing, I'm presenting to you a top 8 list of ideas in computer architecture, the most important ideas in computer architecture. Now, a top 8 list is not as satisfying as a top 10 list, but given that I've restricted myself to picking one idea from each decade, I have only 8 ideas. And if you want to see the top 10 version of this list, you have to come back in the year 2040, 20 years from today, to see what 2 ideas I've added to this list. Okay, first, before, sorry, I forgot to mention that the ideas start from the 1940s, the idea of stored program, 1950s, microprogramming. From the 1960s, I've chosen parallel processing. 1970s, cache memory. 1980s, pipelining. 1990s, FPGAs. 2000s, GPUs. And 2010s, specialization. So I'll go over these in turn, but before, let us discuss for a few minutes what came before the 1940s. Well, the idea of a computer that can be programmed dates back to Babbage's difference engine. In fact, difference engine could be programmed in a very limited sense. It had a fixed program, essentially. And it could compute polynomials. Here I've shown a very simple example. Babbage actually used a 7th degree polynomial. So if I want to evaluate this polynomial x squared plus x plus 41 for different values of x, one way to do it is basically to use a squarer or a multiplier to compute x squared, then add to that the value of x, and then add 41. So 1 multiplication and 2 additions. But if I want to compute this function for a whole bunch of values of x, there's an easier way that does not involve any multiplication. Now, in the days of Babbage, adders could be designed fairly easily. Even then, you know, the adder was a huge machine if you wanted to have a lot of digits in it for accuracy. But we can use the idea of differences to reduce the entire computation to just additions. So suppose I have f of 0, f of 1, and f of 2, 41, 43, 47. I compute the differences of successive terms. 43 minus 41 is 2. 47 minus 43 is 4. So this is the first order difference. And then compute the difference of these differences. 4 minus 2 is 2. And if I continue this, I notice that the second order difference is a constant. This is sort of the discrete counterpart of the second derivative of this function being a constant. So this column is just 2's. So the values in this column can be easily computed by simply adding 2 to the previous entry. 4 plus 2 is 6, 6 plus 2 is 8. And the values in this column can be computed by adding this first order difference to the previous value. 41 plus 2, 43 plus 4, 47 plus 6, and so on. So all these values of this function f of x can be computed by just additions. Addition of 2's in this column and addition of these d1 values in this column. So this is basically a glorified computer that just does these additions very accurately and very fast for its time. Of course, Babbage later invented the analytical engine, which was a real programmable machine. Neither the difference engine nor the analytical engine were actually built in Babbage's time. Later, people actually took Babbage's design, blueprints, and built these machines, and both of them worked with very minor modifications. There were some minor errors and problems that had to be fixed. And now versions of these machines are available in several computer museums, that one can go and look at. And in fact, the difference engine, the last time I saw it was in the Computer History Museum in the San Francisco area. And somebody actually came and used this in operating condition, used this and demonstrated the computations of the difference engine. Charles Babbage himself, and also Ada Lovelace, who is sometimes known as the first programmer, wrote programs for this machine. As I said, even though it wasn't built, they actually constructed programs that later proved to be correct programs that would run had the machine existed at the time. Then came a whole bunch of electromechanical and what are known as plug programmable computing machines. Plug programmable means that the programming of the machine is done by plugging pieces of wires into various sockets or holes, and by different connections you could program the machine differently. Okay, so with this brief introduction to what came before, let me start with the 1940s, where the concept of stored program was introduced. In this very interesting book, Who Invented the Computer?, the history of legal fights over who actually invented the stored program concept is documented. It turns out that in that legal battle, John Atanasoff emerged as the inventor of the stored program concept. Of course, Turing, Babbage, Eckert and Mauchly, and John von Neumann all contributed to this idea, but the seed of the idea came from Atanasoff, who was sort of a very isolated scientist. He didn't have a lot of connections, but many of the engineers and scientists of his time actually went and visited his lab and came back with ideas. So the ideas that led to the stored program computer came from Atanasoff and his lab. There is no clear-cut first stored program computers. A whole bunch of computers began operation around the same time. In those days, actually, people communicated a lot more about their ideas. Right now, many computer companies tend to hold secrets, and they don't like their ideas to be propagated to other scientists and other labs. But in those days, people communicated freely. So a whole bunch of people actually nearly simultaneously built stored program computers. Okay, so for example, the Manchester Small-Scale Experimental Computer ran a stored program on June 21st, 1948. So in some ways, this can be said as to be the first computer. EDSAC at Cambridge University was fully operational. So when I say fully operational in 1949, means it actually operated before then. So that's why there's no clear-cut first computer. EDVAC was conceived actually in 1945, but not delivered until August 1949. And BINAC was delivered on August 22, 1949, but did not function correctly at the time of its first operation. Okay, from the 1950s, I'm going to pick microprogramming as the key idea. In the 1950s, people were building a lot of different kinds of computers, and in particular, they all had different instruction sets. So because they had different instruction sets, the design of each computer had to start from scratch, and specific hardware built to execute that particular instruction set. Okay, now these different instruction sets cause the computer not to be compatible. That's a different objection, but it also led to high design costs. Now this idea, in fact, there's no controversy about who invented it. Maurice Wilkes actually did that. He noticed that when you execute an instruction in hardware, that execution consists of tiny operations that are performed in sequence. So for example, you first fetch an instruction. No matter what the instruction is, the first thing you do, you fetch it. Then you decode the instruction and perhaps fetch operands from the registers. And then for some instructions, the next thing you do is specified in this circle, and then you are done for those instructions. For other instructions, you go into this path, do some stuff here, and then depending on the instruction being executed, so in this case store word versus load word, you go to different paths. If you go here, you end after this fourth cycle, so you can view each of these cycles as being a clock cycle. For load word, you do 2 more cycles of operation and so on. So this looks very much like a program. You can view these circles as instructions. So there's sequential operation, one instruction coming after another one. There's branching, and there is branching to the beginning where you start executing the next instruction. You fetch the next instruction. So Wilkes said, okay, why program these actions in hardware? Why not treat this as an instruction, so that by putting different bit values in that instruction, we cause these signals. So these are, each of these names is a signal. ALU source X is a signal that is set to 1 when we are in this cycle. Okay. ALU source X is set to 0 when we are in this cycle. Okay. So this led basically to a micro instruction. A micro instruction corresponds to one of these states or cycles, and the bits of that micro instruction tell the hardware what to do. So for example, ALU inputs. Okay, one bit says where the ALU source is, source X. The first input to the ALU comes from somewhere according to the value of this bit. ALU source Y, the second operand to the ALU, comes from 4 possible places depending on the values of these 2 bits. And let's say the ALU is just an adder subtractor, and this signal says whether to add or subtract. And then logic functions are specified by these 2 bits, let's say AND, OR, XOR, and so on, and so on. So these bits, basically, whenever a bit is 1, it causes an action to occur in that particular cycle. And then you simply string these micro instructions together to form what we call a microprogram. So these circles are micro instructions, and this is a microprogram for a very simple computer. So the way microprogramming is implemented is that the micro instructions are stored in a microprogram memory. So when we want to execute a particular instruction, we go to the beginning of the micro instructions for that particular instruction and start executing. So we fetch one micro instruction. That micro instruction controls the data path for one cycle according to the values of these bits. In this particular example, there are 2 bits in the micro instruction, that tell the microprogram unit what to do next. So after this micro instruction is completed, what happens next? And the options include increment the microprogram counter. So that's one option. So if these two bits are 0, 0, then the incremented microprogram counter. This is when we execute things in sequence, like going from here to here, or going from here to here. Or another option is to set the microprogram counter to 0. That's basically when we go to the beginning and fetch an instruction. So that's basically this jump. Whenever an instruction execution is completed, we go to the beginning and start over. And there are two other options whose values come from two tables. And these are basically the instruction dependent options. So for example, if we are in this state, depending on the instruction code, we have to go to this path, or this path. So the micro instruction that we fetch depends on the opcode or instruction code. And that dependency is recorded in this table. Two tables. The reason we have two tables is that in this particular machine, we sometimes have two branches. For example, in this case, there is one branch over here, and then for this instruction, there is a second branch here. So the first branch is encoded in this table, the second branch in this table. Notice that now the hardware of the machine, so there's the data path, which is ALU and other things, but the control part of the machine is generic. It does not depend on the instruction set. There's a microprogram memory, there's a microprogram counter, a multiplexer, and two tables. And depending on what you load into this microprogram memory, different instructions can be executed. So you can basically design your instruction set by loading the appropriate microprogram into the microprogram memory. This is good because then you can build this hardware in very large numbers and then sort of customize it to different instruction sets by simply loading different microprograms in the microprogram memory. From the 1960s, I've chosen parallel processing. Of course, parallel processing is actually older than 1960s. Before we did parallel processing in the modern sense of the term, we had something called associative memories or content addressable memories, which allowed us to search the memory content to find particular patterns in there. And these were available beginning with the 1940s. So you can argue that this is actually a form of parallel processing because the entire content of the memory is searched in parallel to determine which words in the memory match the pattern that we are looking for. The first real parallel processor in the modern sense was the ICCKE22 computer designed at the University of Illinois. So the name ILIAC comes from Illinois. It was an SIMD, single instruction multiple data parallel processor, which means that it had a single control unit that controlled a bunch of processors that would run synchronously. So the control unit would fetch an instruction and then issue control signals to all of these 64 processors. In fact, the initial design called for 256 processors, but eventually, given how expensive hardware was in those days, only 64 processors were actually built. And these processors actually had drum memory, and that's a different story, because even core memory in those days was rather expensive. So to have 64 memories of fairly large size would be too costly. So each processing element or processor basically receives the control signals and either executes the instruction dictated by those control signals or ignore it based on local data-dependent conditions. So this would allow conditional operations to be performed. Some processors would ignore the broadcast instruction. Others would perform it. Later, we devised various forms of MIMD, multiple instruction, multiple data parallelism, where processors were independent and each executed its own programs. I've shown two versions of this type of MIMD parallel processors schematically in this diagram. In one, memory is global, so there are a whole bunch of memory modules that can be accessed by the processors through a processor to memory interconnection network. And because this processor to memory interconnection network can become a bottleneck, given that a lot of processors are trying to access a lot of memory modules at the same time, a cache memory may be provided adjacent to the processor, so that, just like the way caches work, most of the time the processor finds the data it needs in this cache. If it doesn't find it there, it goes to main memory and fetches the data. Of course, when you have caches, and given that these processors share data, it is possible to have multiple copies of shared data in different caches, and keeping those multiple copies consistent is a whole discussion that I won't go into. So caches solve the bandwidth problem for this processor to memory network, but create a different problem, which is keeping multiple copies of data in caches consistent. A second version of this MIMD parallel processing is each processor having a private memory, and then all the processors connected to each other through an interconnection network. So the way we devise algorithms for these computers is that we try to write the program, the code for the processor, and distribute the data to these memories, so that most of the time processors access local memories. Occasionally they will have to go to remote memories, and that would take longer time to access depending on where the data is. So local data is accessed quickly, remote data takes more time, and in fact the time may be dependent on where exactly the data is located, and it also depends on the structure of this network. You may have heard of the concept of memory wall. And nowadays processors are extremely fast. Memories have not improved in speed by the same order of magnitude. So even on a single processor system, the memory is a bottleneck. So memory access time dictates how fast we can execute instructions. So imagine that now if the memory is accessed not just by one processor but by multiple processors, the memory wall becomes even taller and will hurt performance even more. So a lot of different techniques are used in the design of parallel processors to remove or at least reduce this bottleneck. Okay, so supercomputers nowadays are all parallel computers. Okay, the largest supercomputers in the world nowadays have on the order of several million processors. Okay, the days are gone since we could provide high performance in a single processor. We can have a high performance single processor, but the types of performance that we talk about nowadays, multiple petaflops, and most recently we have achieved an exaflops of performance. That's 10 to the 18 floating point computations or operations per second. And those cannot be done on a single processor. In fact, we have millions of processors. Now, the supercomputer has been shrinking in size. An old supercomputer had an equivalent computational power to Sony PlayStation. So this was a 1997 supercomputer. The Sony PlayStation, built in 2006, offered comparable performance, about the same as this huge supercomputer. And now we have iPhone 13 or iPhone 14 more recently that offer almost the same performance as this Sony PlayStation. Of course, they're optimized for different types of applications, for image processing, video streaming, and stuff like that. But roughly speaking, in terms of computational powers, an iPhone 13 is equivalent to a supercomputer of a 25 years ago. Now this slide I always show in my parallel processing classes. I first designed this slide in the year 2000, and in 2000 I told my students that we now have gigaflops of performance, 10 to the 9 floating point operations per second in our desktops. We have teraflops, 10 to the 12 floating point operations per second in our supercomputer centers. And at that time, the year 2000, we were working on a computer that would achieve 10 to the 15 floating point operations per second, or petaflops. Well, in subsequent offerings of the course, let's say in 2010, all these numbers had been multiplied by 1,000, 10 to the 3. In 2010, we have teraflops in our desktops, petaflops in the supercomputer center, and we were working on exaflops computers. In 2020, we have almost petaflops on our desktops. For example, NVIDIA's AI chip offers about that level of performance. Exaflops in the supercomputer center, roughly speaking, actually exaflops was achieved in 2022, not quite in 2020. And we are now working on zetaflops performance, 10 to the 21 floating point operations per second. From the 1970s, I've chosen the idea of cache memory as the most important idea. Again, the idea of cache was actually proposed in 1965 by Maurice Wilkes, the same person who proposed microprogramming. However, in the 1970s, actually, the idea caught on, and computer manufacturers started actually implementing cache memory. So the idea is older a little bit. IBM 360 Model 85 was one of the first computers to implement cache memory. So what is a cache memory? A cache memory is basically a small memory that sits between the CPU and main memory. I mentioned before that main memory is super slow compared with the CPU. So the CPU does its operations in a fraction of a nanosecond these days. Memory, if you have a large memory, the access time to the memory is around 100 nanoseconds. So much, much slower. So we put a faster memory, actually, excuse me, a faster memory. Nowadays we have multiple levels of caches. Between main memory and CPU, the idea is that we move the most frequently used data into these faster memories so that the CPU most often finds the data that it needs in these fast memories, so it can access them quickly, only occasionally. So a typical hit rate in the cache is 98%, 99%, which means only 1% or 2% of the time we have to go to main memory. So that slow speed of main memory does not hurt the performance too much, given that we don't access it frequently. Okay, so I'd say here that Harvard architecture is used for L1 or level 1 caches, meaning that the data cache and instruction cache are separate, and the von Neumann architecture, shared memory, is used for L2 and L3 caches. So we have the concept of memory hierarchy these days, where the fastest memory a CPU has access to are registers. Those are accessed in the same time frame as instruction execution time, so a few nanoseconds. Then cache 1, cache 2, sometimes cache 3, then the main memory, then secondary memory, which is typically a mechanical disk, magnetic recording disk, and often nowadays it's also solid state disk, which is much faster, and tertiary memory, which is basically the archival memory. And as we go down this pyramid, the capacity increases and the speed decreases. The cost per byte also decreases. So that's the idea of memory hierarchy. The bulk of our memory is slow, but also very cheap. Small part of the memory, registers and cache, is fast, but also fairly small because it would be very expensive if we try to implement large memories with flip-flops, as we do for registers, or with SRAM, fastest possible SRAM, as we do for cache 1. So here's an analogy to understand the concept of cache memory. Suppose I'm sitting at my desk and working and stuff, and let's say I'm preparing a lecture for my next class. On top of my desk are all the stuff that I need in order to prepare that lecture. Of course, this is an old slide that I made. You see, there's no computer or laptop on my desk, so I'm working on with paper. There's a textbook, there's paper on which I have my notes. Then stuff that I need for the same course, but not necessarily for today, may be stored in a drawer here. And the archives for this particular course that I'm teaching, computer architecture, is in the file cabinet. Okay? So as I'm preparing my lecture, most of the time I consult the textbook and my notes here. So let's say I can access that in about 2 seconds, quite fast. Sometimes I have to go to the drawer. That takes a little bit longer, 5 seconds. And on occasion I have to look up something from the old file, so I have to walk this cabinet, which may be in the next room, adjacent room, so it takes longer. So these are basically analogs of registers, cache memory, and main memory. So the average access time to a document is dictated mostly by this axis, because if 90% of the time what I need is here, so 90% of the time I pay only a delay of 2 seconds. And maybe if the remaining 10%, let's say 8% is here, I pay a little bit more. I suffer a little bit more delay. And only in 2% of the time I have to pay this long delay to get the document. So the average access time is much closer to 2 seconds than to 30 seconds. So that's the idea of cache memory. So a cache memory works according to the locality principle. The reason it works is that our accesses to data tend to be local, and there are two types of locality. One we call temporal or time-wise locality, one we call spatial or space-wise locality. So this is a particular program running. This is from a paper by Peter Denning. And this is the address space of the program, and the horizontal axis is time. So as the program progresses in time, it accesses various parts of its address space. So you notice here that for a significant period of time here, the program accesses these addresses in this range and also these addresses. It doesn't access anything in this area, anything in this area. Okay, so I've put a significant portion of this data in the cache memory. Then for a significant period of time, everything I need will be in the cache memory. So when I put something in cache memory, I typically bring a chunk of data, not just one word, into cache. And because whenever I need a particular address, I often need also nearby addresses. This happens, for example, when I'm accessing elements of an array. So when I need one element of the array, I may need the adjacent elements. And therefore, when I bring a chunk of data into cache memory once, that satisfies a whole bunch of accesses for many cycles after that. And this is known as spatial locality. So accesses are bunched together or clustered together in space. Similarly, accesses are bunched together in time, meaning that if I need a particular piece of data at this point, I may need it a little bit later, a little bit later. At some point in this example, I lose interest in that piece of data. The program moves on to do other things and never accesses that data again. So if that data is kicked out of the cache, okay, there's no problem because I'm not going to access it. So multiple access to the same piece of data are bunched together spatially, temporary in time. Okay, and these are the two principles that make cache memory work. So here's a summary of memory hierarchy. We have registers, we have cache, we have main memory. As I just mentioned, when you bring something from main memory, which is very slow, into cache, you just don't bring the word that you need, you bring a chunk of data, a block of data from main memory. So with one access to main memory, you bring multiple words, so that in the later cycle you may need this other word, you may need this other word, and so on. And then if we implement virtual memory, we bring pages from the secondary memory into main memory. So I've shown here 3 pages. So page is a larger unit of data. So here I have words in registers and in cache. Then I have blocks in cache and main memory. And I have pages that are units of transfer between main memory and secondary memory. So collectively, these memories provide the illusion of high speed and the illusion of high capacity. So high capacity is provided by this disk, and high speed is provided by registers and cache. And because most of the time I find my data in this fast area of the memory hierarchy creates the illusion that this huge memory is also very fast. Of course, the idea of caching nowadays is used in other contexts, not just between processor and main memory. We have something called disk cache. Again, disk is almost infinitely slower than the processor. So we talk here about many milliseconds, not nanoseconds. So processor operates the order of nanoseconds. Main memory is about 100 nanoseconds. And disk memory is 10, 20 milliseconds. That's an eternity. So the way modern disks are organized is that when you need a particular sector, you don't read just that sector. You maybe read the entire track containing that sector, because it doesn't take much longer to read the entire track than to read that sector, because to read that sector you have to move the head and then you have to wait for the disk to rotate until the data is aligned with the read-write head. On average, you have to wait excuse me, you have to wait half a disk rotation. Okay, sorry about that. With one rotation of the disk, I can read this entire track and move it into the disk cache so that all the other parts of that track will now be accessible to me at the speed of DRAM, which is much faster than disk speed. Now, pipelining again was used much earlier, but in the 1980s it gained widespread applications in vector processors. So a vector processor has function units that are pipelined. So these may be a multiplier, an adder, a divider, whatever function units, and a bunch of vector registers, let's say 64 entry vectors, can be stored in these registers. So then we can perform vector operations. So we can take two vectors and add them element by element. So the first element of this vector added to the first element of this vector, and the result stored in a different vector. And these elements are pipelined through this. So by the time that the first addition, let's say, gets to the end of this pipeline and it's stored, I'm doing, so this is the first addition, the second, the third, the fourth, the fifth, the sixth, seventh. So 7 additions are in progress at the same time. So this is basically the idea of vector processing. Of course, memory can still be a bottleneck, so these vector processors were designed to have very efficient memory interface. So there's a load unit that allows us to load a vector into this register. A second load unit that allows us to load into this register. And a store unit that simultaneously allows us to store the values from a third register into memory. Okay, this diagram basically the same thing, maybe a little more clear. So we have 6 vector registers. Let's say we are operating on vector register 0 and vector register 2 and storing the result in vector register 4. At the same time, we are loading data into vector register 1 for the next phase of the computation. So we overlap memory access with computation. We are loading something into vector register 3 and we are storing the result of a previous computation that is in vector register 5. So I'm so sorry. I've had a bad cold for the past week and I'm still recovering. So a lot of overlap. Data loading, data storing, and computations all occur at the same time. So this is pipelining the way many of you may have seen in textbook. This is an instruction execution pipeline where the instruction is fetched in one cycle, registers are accessed, and the instruction is decoded in the next cycle. ALU operation is performed in the next cycle. The data cache is accessed or loaded in the next cycle, and finally the results are written back into register file. So this is one instruction. This is the next instruction that follows it one cycle later. Once this one is done with its fetch, the next instruction does its fetch, and so on. Of course, in general, we have dependencies between these instructions. So it's possible that this instruction has some data dependency on the previous instruction, so that we may not be able to initiate it before this instruction has been completed, or at least partially completed. So here I've shown an example of that. Here the contents of register 8 and register 6 are added, the results stored in register 8. The following instruction uses the contents of register 8 to do some addition. Okay? So there's data dependency between this instruction and the previous one. The result of this instruction is used as an operand by the next instruction. So as this instruction executes, the ALU computes the sum, but that value is not stored in the register until 2 cycles later. Meanwhile, this next instruction needs the contents of register 8 right here, because it has to be fed to the ALU. But that value will not be available until here. And this is solved by something called data forwarding. It's an interesting discussion in computer architecture. You basically detect this dependency. There's special hardware to detect that dependency. And the hardware recognizes that what we need here as input to the ALU was computed by the previous instruction at the output of the ALU, and it simply forwards it. In due course, the value will be eventually recorded in the register too, but meanwhile we use that value, sort of intercept it on the fly and use it here. Of course, if pipelines are deep, such data dependency may not be resolvable through forwarding. Here I've shown a case where the output of the ALU in this instruction is needed as the input of the ALU in the following instruction. But this need occurs one cycle before that is produced, and therefore forwarding, you can't go backward in time. Therefore, you have to delay the execution of this instruction by one cycle so that we can forward from here to here. So imagine everything in this row moved one cycle to the right. And that's sometimes called inserting a bubble in the pipeline. Delay instructions so that data dependencies are honored. Okay, from the 1990s, I've chosen FPGAs. Of course, something similar, the same idea of arrays of logic gates, has a long history going back to 1970s. But in 1990s, we were able to build gate arrays that were complex enough for us to be able to do a lot of interesting things on them. So an FPGA consists of logic blocks, a bunch of programmable connections, programmable in the sense that these dots are sort of fuses that allow you to connect these two lines together or disconnect them from each other. And therefore you can connect the logic block to another logic block through these programmable connections and through switch boxes. So for example, this signal can come here. Let's say I program this one to establish connection. So it goes into the switch box. From the switch box, again, I use settings so that it is directed to this output of the switch box. And then from there, I program this connection so that it goes. So it's a very flexible way of implementing hardware. In fact, modern FPGAs are so complex, they have so much logic and so much connections, that you can implement an entire CPU on it using a small fraction of the resources that it has. So it may have thousands of logic blocks, and you may use maybe, a couple hundred of them to implement a full CPU and still have resources left over to build other stuff on that FPGA. FPGAs are everywhere. Our typical cell phones contain an FPGA. The nice thing about FPGA is that because it's programmable, if you want to update your hardware, you just simply upload a different program into your FPGA, and that modified hardware or updated hardware will be implemented. Okay. From the 2000s, the concept of GPUs I've chosen as the main idea, most important idea. Again, graphics, so the GPU stands for Graphic Processing Unit. The idea of Graphic Processing Unit goes back to the 1970s when we first started building computers that required us to generate pictures, images for the display unit. So we needed a lot of graphic processing capability. But in the early 2000s, the two major players, ATI and NVIDIA, produced powerful chips to improve the speed of shading. And these GPUs eventually turned into what we call general purpose GPUs. So they were no longer just optimized for graphic processing, but they could do a lot of different computations. And these general purpose GPUs are now integral parts of the highest performance computers that we build. I mentioned that high performance computers have millions of CPUs. Well, they're actually not all CPUs. Most of them are GPUs, because GPUs are more efficient in doing arithmetic operations, and they also use less power. So it makes sense to use GPUs instead of CPUs. We still use some CPUs, but most of the units on a high-performance computer are actually GPUs. Okay. So here is, this is a rather old diagram, but it sort of shows you the trend of performance for GPUs in gigaflops compared with CPUs. So these blue lines are CPUs. Okay, the CPU single precision, floating point computation, CPU double precision. So this is how much over the time 2001 to 2013 roughly CPUs improved in terms of gigaflops. In the same time frame, GPUs grew much more rapidly in terms of performance. Similarly, in terms of data rate, data access rate, again, GPUs outperformed CPUs by a significant margin. So that's why GPUs have become popular components in building supercomputers. And we can do general purpose computing on GPUs. So GPUs are no longer just graphic processing units, but they're really high performance numerical chips. Okay, so this takes us to 2010s. Okay, I still owe you a brief discussion of the 2020s, my predictions for what will happen. I've classified these ideas or advances as methodological advances and performance improvements. So parallel processing, cache memory, pipelining, GPUs can be viewed as techniques to improve performance. And stored program, microprogramming, and FPGAs can be viewed as new methodologies for designing computer architectures. So here I've shown the contributions of these methods and some other methods that I have not discussed to performance improvement in computer systems. So pipelining contributed a factor of 3 to 8, depending on how you use it. Cache memory contributed a factor of 2 to 5. Hardware acceleration, for example, GPU, contributed a factor of 2 to 10. Vector and array processing, another factor of 2 to 10. In parallel distributed computing, a wide range of, depending on how many processors you use, it can go into the thousands. Now this diagram gives you a very interesting overview from about 1985 to 2010 as the feature sizes shrank in integrated circuits from 1.5 micron down to 0.032 micron or 32 nanometers. We roughly experienced a 10,000-fold improvement in performance. Of that, a factor of 100 can be attributed to faster technology. Basically, our gates and integrated circuits became faster. So even if we didn't have any architectural innovations, everything would be running about 100 times as fast. Another factor of 100 resulted from architectural innovations, some of which I discussed in the previous slides. And in fact, the bulk of improvements, if you see the slope of improvement, was greatest in the period 1995 to 2000. It has somewhat flattened since then. So in 2010s, we started specializing circuits. Up to the 2000s, we tried to make everything as general as possible. So for example, FPGA is a good example of that. An FPGA is a general circuit with which you can do almost anything you want. The notion of programmability is also a concept of making things general and then programming it to do specific things. But now we have reached sort of the end of the road in improving performance using those strategies. So going from CPU to GPU, we have some specialization. It includes improved performance and power efficiency. From GPUs to FPGAs, again some more. Now the trend nowadays is to use ASICs, application-specific integrated circuits, because those can be custom designed to be very fast and very power efficient. Of course, they're also quite expensive to build. Okay, So if you're building something that goes into, say, the iPhone, and then you build many hundreds of billions of iPhones, then it makes sense to invest a large amount at the beginning to develop this ASIC. But then producing additional copies of that ASIC is not very expensive. If you use FPGAs, the initial cost is low, but then if the volume increases, you have to pay more. So ASICs make sense for high volume production. You don't build an ASIC if you are just building a single system. Doesn't make sense. So in 2017, Hennessy and Patterson, who are well-known computer architects, and they have a very famous computer architecture textbook, they received the ACM Turing Award. And in 2018, they gave a lecture entitled A New Golden Age of Computer Architecture. And in that, they basically said further progress in conventional architectures is impeded by its slowing Moore scaling, end of Dennard scaling, that's basically power efficiency, and diminishing return at high energy cost for ILP. This is instruction level parallelism. So instruction level parallelism can no longer be exploited efficiently anymore. Okay, so they advocate domain-specific languages to go along with domain-specific architectures, and also free open architectures and open source implementations so that people can collaborate in improving an architecture, rather than having closed architectures so that we can't do anything at the user side to improve those architectures. Okay, so an example of a domain-specific architecture is Google's Tensor Processing Unit. Tensor Processing Unit is basically something that is optimized to do matrix multiplication. And matrix multiplication is a very common operation in machine learning, and therefore these tensor processors tend to be very efficient in running machine learning applications. So this is sort of an ultimate in GPU. We have many hardware units, and an efficient way of pipelining data through those hardware units so that matrix multiplication is done very efficiently at high speed and at high data rate. Okay, looking ahead, here are a few of my predictions. Of course, predictions are hazardous in the area of computer engineering. The literature is filled with what now seems very funny predictions by experts in the field of computing that were way off. It's very hard to predict even 20 years ahead in computer architecture. So with that caveat, let me give you a few predictions what will happen in the 2020s, a decade that we just started. We will have adaptation and self-optimization of systems through learning. So machine learning will basically be applied to hardware so that as we run programs on the hardware, it learns and it optimizes, self-optimizes itself to be more efficient. Security needs a lot of work. Computer security is in a very sad state nowadays. Reliability through redundancy and self-repair is another area that we need to work on. Logic in memory designs, basically the memory wall arises because the common way of processing data is to take it out of the memory, put it in a processor, do something to it, and then store it back in memory. So new ideas basically try to process data in memory. We don't have to remove it from memory, but locally in memory, we can do at least some simple processing operations on data without taking it out of the memory. And finally, analog design is back in fashion. So mixed analog digital design style is something that we are working on in order to improve the performance and energy efficiency of computer systems. A lot of things in nature are actually analog. So when you try to mimic the nature, something called biologically inspired computing, we tend to use analog computation. So for performance improvement, we have revolutionary new technologies, much denser and much faster than we have been using until now. We are looking for new computational paradigms, brain-inspired and biological computing. I already mentioned that. Things like speculation and value prediction. In other words, try to predict where the computation will go and pre-compute values so that when we need them, they're already available and we can use them. And finally, better performance per watt to remove the power wall that basically makes our supercomputers nowadays use megawatts of power. So a supercomputer has to be next to a power generation facility in order to provide it with the amount of power that it needs. So we need to reduce the power consumption both at the supercomputer end and also at the personal devices end in order to make our batteries smaller and last longer. Okay, so let me skip a few slides and end my talk at this point. Oh, let me just go back, sorry. We need more than sheer performance. Okay, for many years in computer architecture, we worried about performance. Then later, we also worried about power efficiency. So power efficiency became a key factor in design. And now we are worried about the environmental impact of these huge supercomputer centers that use megawatts of power. They pollute the air. Furthermore, we use cell phones for a few years and then throw them out. Many of the components of cell phones cannot be recycled, so they lead to environmental problems. Now, since 2016, ICCKE has been publishing the Transactions on Sustainable Computing, and I've been an editor of that publication since its establishment in 2016. And the idea is that come up with new methods to make computing more sustainable, more environmentally friendly. So performance, of course, still important. Energy efficiency is important, but sustainability is emerging as an important consideration in designing computer architecture. Okay, thank you very much for your attention, and I'm looking forward to answering your questions during the in-person session.